In the third section on this second part of the course on mechanical vibration, we'll look at the 1 degree of freedom spring mass system, and we'll look at different types of excitation: external force excitation, base excitation, rotational unbalance, and we'll look at the engineering implications, and then finally we'll look at the accelerometer and its dynamics. What you see over here is a mass spring system that is subjected to an external force F of t, and we've seen previously that you can write the second law of Newton to obtain a description of the system. If you go then to the Laplace domain, you can write the transfer function from external force to displacement, and this transfer function is actually called the displacement transmissibility or compliance. And remember that for damping ratio zeta smaller than 1, well, the behavior that you have is that of an underdamped second order oscillatory system. We had seen previously that when omega is much smaller than the natural frequency, the system actually behaves as a gain, right? And it behaves like, well, the static gain, of course. So we see that when the frequency is small, the displacement is inversely proportional to the spring stiffness constant, and it's independent of the mass. When the frequency is much higher than the natural frequency, that we had seen that this displacement transmissibility goes down as 1 over omega square, and that it's actually minus omega n squared divided by omega squared times the gain, which is 1 over k. Since omega n squared is equal to k over m, well, this can be written down like this. So we see that the displacement transmissibility is inversely proportional to omega squared, but it's also inversely proportional to the mass and independent of the spring stiffness constant k. We had also seen that at a natural frequency, the displacement transmissibility is actually dominated by the damping ratio. When this damping ratio is very small, well, you have a huge displacement transmissibility. We had already seen for our second order oscillatory system that you can write the modulus and the phase shift as a function of the normalized frequency. And here in a mass spring system, you know that the static gain is 1 over k. So the displacement transmissibility for this kind of system is the same as the one that we had obtained, with this 1 over k appearing here at the numerator. And this is why very often, instead of the displacement transmissibility, we are going to use the normalized displacement transmissibility. It's the same as what I've got here, but times k, so that this one here disappears. So here we have our normalized displacement transmissibility. Don't forget that if you want the displacement transmissibility, you have to multiply by 1 over k. So this will cause a shift in this part of the Bode diagram. But remember that in low frequencies, well, this normalized displacement transmissibility is 1 or 0 dB. There is hardly any phase shift. Okay, so this is the behavior for omega much smaller than omega n. At the high frequencies, well, you got 180 degrees phase shifts. You got a slope here of minus 40 dB per decade. And if your R is increasing, well, you'll have a displacement transmissibility that will go down. And we've seen that at the natural frequency, which is R equal to 1, you have a phase shift of minus 90 degrees, and that the displacement transmissibility is dominated by zeta. So if zeta is small, you will see that you have here a huge response. So remember here when omega is low, it's essentially the displacement transmissibility is essentially dominated by k. Okay, here it's essentially dominated by m, and here it's dominated by c or zeta. Well, previously we have been looking at the displacement transmissibility, but there is also a force that is transmitted to the support that is over here, right? And we can look at what is called the transmitted force. Okay, so we're going to look at another transfer function, which is input the external force and output the transmitted force on the support. Well, it's very easy to see that the transmitted force is linked to the displacement by this equation, and since we had already computed the displacement transmissibility, okay, remember that this is indeed the same equation as I've written before, 1 over k s squared plus c over m plus k over m, okay, and this is omega n squared, and this is 2 zeta omega n. So this is indeed the same equation. When you combine these two, okay, you arrive at a force transmissibility which has this expression here. Okay, if you divide by m, you'll end up by c over m s plus k over m divided by s squared plus cm s plus omega n squared, or k over m. And this can indeed be rewritten as this transfer function. So we have now obtained what is called the force transmissibility. Okay, this force transmissibility can be rewritten in terms of the normalized frequency, and we play the same game as before. We replace s by j omega. We write everything in terms of r, which is the normalized frequency omega over omega n. When we do this, our transfer function becomes a complex number, and then we can look at the magnitude and we can look at the phase shift, and you obtain two expressions, one for the magnitude of the force transmissibility and another one for the phase shift of the force transmissibility. Well, this is the force transmissibility that we had obtained in the previous slide, and we see that it is 1 if this term is equal to 1. If it is equal to 1, you see that this ratio is 1, and of course this transmissibility force transmissibility, sorry, is 1. So a condition for this to happen is that this quantity is 1, and if you do the computations, you will see that there are two solutions, r equal to 0 and r equal to square root of 2. Just plug it in and you'll see that. And you can see that this force transmissibility is higher than 1 in this region in between these two roots, 0 and square roots of 2. For r that is larger than square root of 2, or equivalently when omega is larger than square root of 2 times the normal natural frequency, then this transmissibility is lower than 1. We will see also that the force transmissibility in this region, this region here, increases with increasing damping ratio. Well, this is the force transmissibility, and as we've been seeing, when r is smaller than square root of 2, you know that this force transmissibility is higher than 1. So the force that is transmitted to the support is higher than the force that is actually being applied externally, and for R bigger than square root of 2, you see that the force transmissibility goes down. You also see that for increasing zeta, so zeta increasing, the force transmissibility is also going up. I have not talked a lot about the phase here of this force transmissibility, but you can see that it goes to minus 90 degrees at high frequency. This is because you have a relative degree of the transfer function which is 1. You had a degree 1 at the numerator and a degree 2 at the denominator, so the difference is 1, and this implies that at high frequency the phase shift will be minus 90 degrees. Well, we can now start looking at the engineering implications of what we have just seen, and one implication is that, well, if the forcing frequency of your external force, omega f, is close to the natural frequency of the system, you'll have a phenomenon that is called resonance. Okay, and the vibration amplitudes will be high, and they will be even higher if your system is lightly damped, that is, if zeta is small. Engineers try to avoid resonances because large amplitudes, vibrations with large amplitude, well, they imply large forces, and large forces cause failure and damage, right? You know that it's possible to know the forcing frequency of your external force. If it's harmonic, it's quite simple. Sometimes the force is not harmonic but periodic, but you know from the course on signals and systems that you can use the Fourier analysis, and that you know that you'll have components at frequencies which is of course the fundamental but also the harmonic, so you can kind of see if your forcing frequency is close to the natural frequency. With what we have seen before and knowing the forcing frequency omega f and the amplitude of your external force, it's possible to predict the amplitude of vibration and the force that is being transmitted to the support, so you can use that for design. But a word of caution, because everything that we've done is based on a Bode diagram, so we assume that we are kind of in steady state. So we have neglected all transient effects. Okay, remember that it's often during the transient effects that the peaks of vibration are obtained, right? And often they are much higher than during steady state, so you should take that into account in your design. Well, in this slide here I show you the normalized transmissibility that we've seen before, and the force transmissibility. Okay, and it's as a function of r here, and r is omega over omega n. And what you see here is that if you use r larger than square root of 2, well, you're in the so-called isolation region. This means that your normalized displacement transmissibility and your force transmissibility will be smaller than 1. Okay, usually we'll take r much larger than square root of 2. Remember also that in the force transmissibility, well, if you take zeta that becomes smaller, well, the force transmissibility becomes smaller as well. Well, to run the system in the isolation region, we have to make sure that r is bigger or larger than square root of 2, and we should actually say much larger than square root of 2. And one way to do that is, of course, to make omega n, the natural frequency, as small as possible. So omega n is equal to a square root of k over m. So we want to make it as small as possible. One way to do that is to make it as soft as possible, to use a stiffness coefficient k that is as small as possible. Another way to do that is to increase the mass, okay, using a heavy foundation. And in this way we'll be running in the isolation region. Notice also that in the isolation region, as I said before, well, the transmitted force is smaller, okay, when the structure is lightly damped. For some systems, you'll have not one natural frequency, but you'll have more than one natural frequency, right? So if you run in the isolation region, so you work in this region, so you work about the first natural frequency, well, you run the risk to choose a forcing frequency that is close to this second and third natural frequency, and this will cause resonance, okay? So that can cause difficulties. One comment that I have to do also is, of course, if you want to work, suppose that you only have one natural frequency, and you want to work in this region over here, and suppose that this is a bit more lightly damped. Well, to arrive in the isolation region, when you stop your machine, you have to go through the natural frequency, okay? And this can create dangerous large amplitude vibrations. You have to do this as fast as possible. For those systems where the forcing frequency might excite higher order resonance frequencies, like I'm drawing over here, this is your first resonance, your second resonance, and your third resonance. Well, you have to work in the subcritical frequency range. This means that you have to work in this region of frequencies, which is characterized by a forcing frequency which is smaller than the natural frequency, the first natural frequency. Okay, in this region, you also know that in steady state, when the forcing frequency is small enough, the gain will be 1 over k. Okay, so we're considering here the displacement transmissibility. So if we want a small displacement, you have to work with a value of k that is large, so that this 1 over k value becomes as small as possible. The advantage of working with a k that is large, of course, is that this natural frequency will shift to the right. Well, the downside of working with this stiff structure and with forcing frequencies that are lower or much lower than the natural frequencies is that, of course, the external forces are transmitted one-to-one to the support. Well, let us now take a small example of what we have just seen, and we consider a structure that is idealized as a spring mass system with a stiffness of 10 kilonewton per meter, a damping coefficient of 2 kilonewton second per meter, and a mass of 2000 kilos. And this system is subjected to a harmonic force of 500 newton at 0.5 hertz. And the question is, can you compute the steady state vibration amplitude? Well, since we have the values of K, M, and the damping ratio, not the damping ratio, but the damping coefficient C, we can compute the natural frequency omega n and the damping ratio zeta, and we can see here that in view of the damping ratio, well, our system is lightly damped. We know the forcing frequency expressed here in hertz, so we have to bring that back to something expressed in radians per second, and we can now compute the normalized frequency, which is approximately 1.4. Well, since we have now computed the normalized frequency, we can plot the normalized displacement transmissibility and look what displacement or what normalized displacement transmissibility we have for r equals 1.4, and we see that this normalized transmissibility expressed in dB is around 0.16, so we know that this normalized transmissibility is in the neighborhood of 1. We can now compute the magnitude of the displacement by multiplying by f and divided by k, so 1.02, let's say, times the force, and that has magnitude 500 divided by k, which is 10,000. This gives us a displacement magnitude of 50.9 millimeter. Well, now we'll consider a different case where we have base excitation. Okay, so this is a practical situation that can occur, for instance, where a car is subjected to vibrations caused by the road profile, or that a building is vibrating during an earthquake. From Newton's equations, you can derive the equation of motion using Newton's second law, and the difference is now that you don't have any external force. Okay, so mass times acceleration is the net force. You have the restoring force coming from the spring and the damping force, and the restoring force looks at the difference between y and x, and you have something similar for the damping force, but with displacement replaced by speed. So you look at the speed differences. Well, we had seen in the previous slide that mass times y double dot was minus k y minus x minus c, and then y dot minus x dot. You can rewrite this as m y double dot plus c y dot plus k y is equal to c y dot, no, not y dot, but x dot plus k x, right? If we go to the Laplace domain, you generate the variables y of s and x of s. X of s is the input, it's the base excitation, and y of s is the displacement of your mass. And you can now compute a new transfer function, which we will call the displacement transmissibility, but in the case of a base excitation. This transfer function, if you divide by m, becomes c over m s plus k over m divided by s squared plus c over m s plus k over m. This is omega n square, and remember that this is 2 zeta omega n, and you arrive at this expression of the displacement transmissibility. This might look familiar to you, and indeed it is, because it's also the force transmissibility, but in the case of a problem with external force excitation. Well, again, we can see what happens if we work with this normalized frequency r, which is omega divided by the natural frequency, and then we can look at the displacement transmissibility and compute the magnitude and the phase shift of this displacement transmissibility, and we obtain expressions that are exactly the same as for force transmissibility in the case of an external force. So of course the displacement transmissibility looks familiar in the case of a base excitation, and you see, as we had computed previously here, is that if r is smaller than square root of 2, the base excitation, in the base excitation case, the displacement transmissibility is larger than 1. Okay, and this is the calculation that we had done to prove that. It's exactly the same calculation that we had done for force transmissibility in the case of external force excitation. Well, just as for the case with an external force, we are interested in the force transmissibility in this case of base excitation. So we are looking here at the transmitted force, and by action reaction, well, it's the restoring force and the damping force. The restoring force coming from the spring, and from the equation of motion that we've written previously, we know that it's equal to my double dot, right? So this is in the time domain. If we're going to the Laplace domain, we can write that the transmitted force, it's the displacement times m times s square. You see here the double derivative. Of course, we are interested in the magnitude of this transmitted force, so we replace s by j omega, we take the magnitude, and we obtain this expression here. We want an expression as a function of r. We know that omega square is omega n square r square, so it's also equal to r square k over m, right? This is an expression for the natural frequency squared. So if we plug that in, we obtain this expression here of the transmitted force as a function of the normalized frequency r. We can now compute the magnitude of the force transmissibility using this expression, where r is the normalized frequency. Very often we use a normalized force transmissibility in the sense that we find this parameter annoying, so we bring it over here, right? And we obtain the normalized force transmissibility. Well, unlike the displacement transmissibility, the force transmissibility goes up as r is larger than square root of 2. This is because of the term that you have, or the factor that you have over here. And you will also see that when the damping increases, this force transmitted increases dramatically when r is larger than square root of 2. This is what we see in the following Bode diagram. It's only the magnitude part here of the normalized force transmissibility. You see that when r is larger than square root of 2, when you're in this region here, well, the transmitted force increases, and when zeta increases, okay, you have that this force that is transmitted increases as well. Okay, here we have the impression that the force transmitted goes to 0 when zeta becomes very small, but at higher frequencies it goes up again as well. Well, we will use what we've seen before, and we'll look at the engineering implications. And the idea is that we want to maybe design a suspension or a vibration isolation system. So we have a mass and a damper spring system, okay, and we have that the base will vibrate with some characteristic frequency, right? And the ultimate goal is to minimize the vibration amplitude of the mass. Okay, so this is valid for suspension design and for a vibration isolation system. Well, this is a summary of what we have seen in the case of base excitation. So on the left you have the displacement transmissibility, and here the normalized force transmissibility. So you clearly see that the amplitude of the mass is minimized if you're working in this region with R that is larger than square root of 2. Okay, you can clearly see that the transmissibility is lower than 1, or it's negative when it's expressed in dB. You also see that the force transmissibility can be quite high, and that it's better to lightly dampen the system, because you see here that the force transmissibility has a tendency to decrease. Well, we have seen that we should work in the isolation region, and we should have R larger than square root of 2, and most of the time we say much larger than square root of 2, or natural frequency much larger than this forcing frequency divided by the square root of 2. So this condition can be achieved here by choosing, as we had also in the case of a forced excitation, small. So we choose a small natural frequency. This can be achieved as omega n is square root of k over m, by taking a small k, a small stiffness or a soft spring, right, or a mass that is actually very large. We've seen that it also helps to lightly damp the system, but a word of caution, of course, is in order, because if somehow the system gets excited and it's lightly damped, well, of course the transients will die out slowly. Okay, and also if the forcing frequency turns out to be smaller than expected, okay, you might have a damaging resonance. And this is what you can see in the previous slide. If your forcing frequency for some reason migrates in this direction here, you can have potentially damaging effects, because the normalized force transmissibility becomes very high. Well, we'll use what you've just seen in a practical example, and the idea is to design a suspension for a car, and this suspension is modeled using this system here, and it's actually a mass spring system. So the idea is, can we compute K, the spring stiffness, and the damping coefficient C, in order to meet some specifications, right? So this car is driving at a speed v over a road that is modeled by a sine wave. Okay, the sine wave has a certain wavelength of 10 meters, and it has an amplitude of 20 centimeters. Well, the specifications tell you that the amplitude of vibration should not exceed 35 centimeter at any speed. Okay, and at a given speed of 90 kilometers per hour, the amplitude must be less than 10 centimeter, and we are told that the car weighs 1400 kilos. Well, we are told that the amplitude of vibration should never be higher than 0.35 meter at any speed. This means that since the amplitude of your input is 0.2, that the displacement transmissibility should never be higher as 1.75 or 4.86 dB. Okay, so what you can do then is draw this displacement transmissibility for a number of values of zeta, which is the damping ratio. And you see that everything is okay if zeta is larger or equal to 0.4. Well, we can now compute the frequency of the base excitation, and we know that frequency is related to speed and the wavelength, and it's actually speed over wavelength. Okay, so we have to compute the speed here in meters per second. This is what we do, and translate the speed from 90 kilometers per hour to something that is expressed in meters per second, and then we divide by the wavelength and we multiply by 2 pi, and we have the forcing frequency. We know that at the forcing frequency, the amplitude of a vibration should never be smaller than 10 centimeter, knowing that the input changes is 0.2 meter or 20 centimeter. This means that the displacement transmissibility at the forcing frequency should be smaller than half or smaller than minus 6 dBs. Well, we see that to obtain a displacement transmissibility that is smaller than minus 6 dBs, we need to take a normalized frequency that is larger than 2, which means that the natural frequency is less than half the forcing frequency, or is less than 7.8 radians per second. Well, we had seen previously that the natural frequency omega n should be smaller or equal to 7.8 radians per second, and that zeta should be larger or equal to 0.4. So we'll take the limiting values. Okay, knowing the expression of the natural frequency and knowing that this is 1400 kilos, you can actually compute the stiffness of the spring of your suspension. And then once you have the stiffness, you can compute the zeta. Okay, you already know the zeta, but you can compute the damping coefficient, right? You know zeta, you know k, and you know m, and you can compute c, the damping coefficient, using this expression, and you obtain now also the expression of the damping coefficient. Well, in this example we'll assume that there is rotational imbalance, that is that the primary source of vibration is in a rotating machine the out of balance of one or more rotating components. We'll suppose that the mass of the rotating part mu is much smaller than m, that the eccentricity is denoted E, and this mass that is out of balance is rotating at a rotational speed omega. We know from the first part of the course that there will be a centrifugal force with magnitude, of course proportional to the mass of unbalance, the eccentricity, and the square of the rotational speed, and of course this will be pointing outwards radially. Okay, so what we can do then is reuse the results that we had for an external force excitation. So we take simply f of t to be equal to the magnitude of the centrifugal force times this sinusoid, right? If we want to write it in terms of R, we know that R is omega over omega n. So we can inject it over here and we have the expression of the external force in the case of a rotational unbalance. We had seen in the case of an external force that the displacement transmissibility was YR modulus divided by F at the normalized frequency divided by its modulus is 1 over k divided by a square root that is exactly the square root that you have over here. In our case, we have seen in the previous slide is that the force is equal to the centrifugal force, and it was in magnitude equal to mu, the unbalanced mass, times the eccentricity times the natural frequency squared times r squared. So if we inject that over here, this is the expression that you obtain for the magnitude of the displacement, and then you can observe here that this quantity here is equal to 1 over m. Okay, so you arrive at this expression of the magnitude of the displacement, where r is again the normalized frequency, and you observe that when r tends to infinity, this factor here tends to 1, and this is why this normalized displacement is often used. Well, this is how the magnitude of the displacement looks like as a function of the normalized frequency. You see that when r is small, or the frequency is smaller than the normalized frequency, you have hardly any displacement. When omega is much larger than the natural frequency, or r is large, well, the normalized displacement tends to 1 in magnitude, and this is irrespective of the zeta. You see that there is very little influence of the damping coefficient, and of course at the natural frequency you have the magnitude of the normalized displacement that can be rather high, especially if the damping is low. Well, we had seen that the normalized displacement was going to 1 for large values of the normalized frequency, or when the frequency is much higher than the natural frequency. This means that the displacement magnitude in steady state for those high frequency values, high with respect to the natural frequency, well, they tend to this value. Okay, and it's obvious that if you want to reduce the magnitude of the displacement, well, you should of course decrease the eccentricity mass. You should of course decrease the eccentricity. If that's not possible, one thing that you can do is take a large value of m. Okay, this can be often achieved by attaching an auxiliary mass to the relevant part of the machine. Well, let us look now at a nice application for an engineer, which is the vibration on a washing machine. Here we have a simplified model for the washing machine, and we assume that the bundle of clothes of 10 kilo is rotating in the machine, and that there is a rotational unbalance, and that the rotating unbalance mass is 4% of this total mass of clothes of 10 kilos. The total mass with the wash is 30 kilos, Okay, so this is the total mass of the machine, and the diameter of the washer basket is 60 centimeter. We assume that the basket rotates at 1200 rpm and that the stiffness and the damping coefficients are given by these values here. The question is, what will be the amplitude of vibration and what will be the force that is transmitted to the horizontal panels over here. So let us compute the rotational frequency, but expressed here in radians per second. Okay, so we have to go from RPM to radians per second, and we obtain this expression of the forcing frequency. The natural frequency is quite easy to compute. It's just the square root of k over m, so we obtain 10 radians per second, and the normalized frequency is the ratio of the forcing frequency divided by the natural frequency, and we obtain here something that is a lot larger than 1, so we know that the magnitude of the vibration amplitude can be approximated reasonably well by this quantity here. So we compute the mass of unbalance, that's 0.4. We multiply by the eccentricity, that's the diameter of the basket divided by 2, and overall mass is 30. Okay, so we see that the vibration amplitude is 4 millimeters. Well, we know that the transmitted force to the horizontal panels is due to the damper and to the spring, so it's the sum of the damping force here and the spring restoring force, right? And here this is done in the general case, but we need the force at the forcing frequency. We are going to replace S by J omega F, okay, and compute the magnitude. Okay, so if we replace S by J omega F, we have a complex number of which you can compute the magnitude, right? And this magnitude is this square root times the magnitude of the amplitude vibration, and if we do that calculations, we obtain a force of 152 newtons. Well, since we are considering a section about the 1 degree of freedom spring mass system, it's a good moment to talk about the accelerometer, and it is by far the most common sensor used for measuring vibrations. An accelerometer is actually a moving mass on a spring and a dashpot attached to a moving object, and the acceleration of the moving object results in a differential displacement x between the mass and the object. Well, as usual, we can write the governing equation using Newton's second law, and this is the equation that we obtain. So we will say that the acceleration of the object is the input and the relative movement of the mass with respect to the object x will be the output, right? And now going to the Laplace domain, and with the usual notations of omega n and zeta, we can write a transfer function from the acceleration of the object to the differential displacement, which looks like this. This is the equation that you obtain in the Laplace domain. It's maybe worthwhile writing it a little bit differently by dividing numerator and denominator by omega n square, and you obtain then this equation here, okay, which is a bit better suited for the analysis that we're going to make. We're going to consider two situations: omega much smaller than the natural frequency and omega much larger than the natural frequency. If we consider this case over here, these terms over here, the two first terms in the denominator, they can be neglected and we obtain this expression here. At high frequencies, well, it's these two terms that have to be neglected, and we also know, since s is equal to j omega, that s square is equal to minus omega square, and we obtain this expression here. So at low frequencies we have that x is proportional to the acceleration. So if you can measure it, you have something that at low frequencies is proportional to acceleration. At high frequencies, okay, well, you know that x, okay, is proportional to acceleration integrated twice, in the Fourier domain. 1 over omega square corresponds to integrating twice, so you know that the relation between x and the position of the object at high frequencies will be 1. So if you measure x and you consider high frequencies, then you have a displacement x that is proportional to the displacement of the object, and you have kind of a displacement measurement. Okay, in this situation at lower frequencies you have an displacement that is proportional to acceleration, so this will be used to measure acceleration, and this is the equation for an accelerometer. Well, this is the principle of an accelerometer. If you consider frequency ranges that are far below the natural frequency, you can say that this displacement is measured and it is proportional, and the proportionality factor is given over here, to the acceleration of the object.